Okay, so in example 8, we are going to be looking at how to graph the greatest integer function. And this is actually a special category of piecewise defined functions. And this is going to be what we call the piecewise defined or the greatest integer function, also known as the floor function. And it consists of a set of discontinuous steps. And we'll talk about why that is. Okay? The way that we notate this is by using these funny looking brackets. So when we're writing this by hand, we'll say f of x is equal to the greatest integer of x. And what those bars tell us to do is to calculate the greatest integer, and recall what an integer is. I can't talk and like spell at the same time. I-N-T-E-G-E-R. There we go. There's the word integer, kinda. That is less than or equal to the input value x. Now, remember what integers are positive and negative whole numbers. Okay? So our outputs are just going to be the integer numbers. Now, the way that we calculate what these are going to be is we take x, and basically you take it down to, if the input value here for x is not already an integer itself, okay, then you take it down to the next biggest integer that is less than your input. So take it down to the next biggest integer. Okay? This kind of idea is used in linear programming. I believe if you want to use a graphing calculator, the TI-84, I think it's this, int x, which is within the math menu. Desmos is going to use floor, and I'll show you that here after we graph this one by hand. On example 8, we want to graph the function defined by f of x is equal to the greatest integer of x. And I think it will be most helpful for us to calculate several ordered pairs, okay, of input values for x and then output values where we calculate the greatest integer of x. Now, to be able to see what happens, y'all, we're really going to have to do some fractions and decimals, okay? I'm just going to put everything in decimal form. So let's talk about like what would happen if x was 0, or what would happen if x is maybe 0.25 and 0.6 and 0.99 and 1. Let's pick those out and you'll see why. And then let's go like 1.3. I'm just randomly selecting some of these. 1.7, 1.999, okay? And then we'll do 2. And then we'll be like, what's 2.1? The greatest integer of 2.1, and so forth. And I think we're going to start to see how the pattern works here. All right. So here, f evaluated at 0 is going to be the greatest integer value of 0. Now that is going to be the greatest integer that's less than or equal to 0. 0 is an integer, so the greatest integer of 0 is 0. Okay? What about the function evaluated at 0.25? We're asked to calculate what's the greatest integer of 0.25. That's going to be the biggest integer that is less than 0.25. We're going to kick that down to the integer 0. Okay? So, I don't want to write all that out every time. I'm just going to show you what's the greatest integer of 0.6. What's the greatest integer that is less than or equal to 0.6? Kick that down to 0. Same thing for the 0.99. What's the greatest integer that is less than or equal to 0.99? That's 0. Notice that we're not rounding here, okay, to calculate the greatest integer. The greatest integer means what's the greatest integer that's less than or equal to that number. Now, when we try to calculate what's the greatest integer of 1, that's just going to be 1. Because 1 is the greatest integer that is less than or equal to 1. Okay? So the greatest integer of 1.3 is 1. The greatest integer of 1.7 is 1. The greatest integer of 1.999 all the way snug up to 2, but not 2, is 1. Then when we get down here and are asked to calculate what's the greatest integer of 2, since 2 is an integer, it's 2. Okay, so do you see why they're calling this also, I like this word right here, the floor function. Okay, because think about all the fractions and decimals as being like spaces from the floor to the ceiling. Well, anything from the floor to the ceiling, it gets dropped down to the floor. Okay? And so when we go to plot some of these ordered pairs, okay, 0, 0, we're going to have a closed circle there. 0.25, 0. 0.60, 0.990, but when we get to 1, it's 1. And so what we need to do down here on this first step is put an open circle at 1, 0. Because when x is equal to 1, the greatest integer is 1. Okay? 1.3, 1, 1.7, 1, 1.999, 1, but when we get to 2, it's equal to 2. So put a closed circle there, but an open circle there. You see how the pattern is now? So to draw in the rest of the greatest integer function, we're going to draw in the rest of these steps with closed circles on the left-hand side, open circles on the right-hand side. We could and then also continue that trend on down here. Open circle on the right-hand side, closed circle on the left-hand side. Okay, we could draw several more of those, but this is the graph of our greatest integer function, the greatest integer of x, or the floor of x. Okay, now what I was saying here is it says on many graphing calculators, the greatest integer function you'll find by saying int of, and inside the parenthesis there you would put the x or whatever it is, if it's 2x or 4x or whatever, and that is found under the math menu followed by the number menu. You'll find that int. Now if you put this into Desmos, lay this microphone down here. If you go to Desmos and you say I want to graph y equals, I need to go find that greatest integer function. So it's over here in this functions thing under the miscellaneous tab. You've got the trig tab for trig functions, the stats tab for stats functions, and the random function. So you can see that there's the floor right there. And so if we're graphing y is equal to the floor of x, you see those steps that come up. Now, here's a problem with some graphing utilities, your graphing calculator included. What is on this graph, or sorry, what is not on this graph, but that should be, are these little nuances of the where's the open circle versus the closed circle. The problem that I'm having here with Desmos is there's not a closed circle here and an open circle here. How are you supposed to know which of these the greatest integer function is defined for? So that is a problem with using graphing utilities, is it won't show you every single thing on your graph. Later on when we get into 3.5, we're going to have holes in our graph. But those don't show up on a graphing calculator is the problem, okay? Also, you see, if you're going to graph this, you should have a closed circle here and an open circle here. If you just graph it like this, I would count it wrong, okay? Because if you think that this point, say, let me pick some stuff up here. If you think that this point is defined, and you know what, so is this point defined, that's incorrect because that would not be a function. These are greatest integer functions because it fails the vertical line test. So that's the big problem. So what you need to do is you need to know, what does this floor or greatest integer function mean, to know that you're supposed to go in here and put closed circles here, ooh, that's big, and open circles here. Closed circles here, open circles here. Closed, open. You know what I mean? Okay? So graphing utilities are great, but they'll only do so much for us in an accurate manner.